Okay, thank you all for interesting talks. I think we covered a lot of ground here, and certainly the infrastructure edge is an interesting topic area. I have a few questions. I've got some individual questions, and I know we've got some audience questions queued up. But one that's come up with several speakers already is the issue of power and availability. We've got a lot of hardware people in our audience. So let's just run down the line here because I think that started with Mike. So Mike, can you comment on TDP and availability of your processor with integrated AI?
Sure. So we haven't publicly announced what our power usage is yet. So as far as the question about what applications, edge applications, so really there's no reason our SoC couldn't be used for any sort of data center environment either. But when we're focusing on these AI and machine learning sorts of applications, that's where it makes the most sense for these edge sort of servers where you don't necessarily want to rely on network connectivity or these big data centers.
Okay, thanks, Mike. Martin, I know, with FPGAs, you don't really talk about TDP so much, but when you're talking about your test cases where you've got kind of, 90% utilization, can you comment at all about power?
I think these devices are sort of going to be around 100 to 120 watts at these type of use densities. Now, we do have some very power-hungry features on board, and it really depends if you're using those or not. And that's going to be those 96 transceivers and those HBMs, of course. Big difference if you're using one HBM stack or two HBM stacks. Anybody who wants to get an idea can actually, this is a 14 nanometer FPGA. It's 700,000 ALMs. There are FPGAs like that, and they can load up the current power estimator in the Quartus tools, and they'll know exactly what type of power to expect from the core, because we do have those devices production qualified and in the tools right now and have been out for a couple of years. This particular device, I think we're about to announce the availability.
Okay, I think that this device is essentially derived from the MX device, which has the integrated HBM. Is that
That's
correct?
right. So you know that it's going to be real, and that's one of the reasons we were able to bring it out so quickly, plus reuse those chiplets.
Yeah, so just a quick follow-on on that. So was the decision to use 14 nanometer purely a time-to-market decision, or are there other advantages over moving to the 10 nanometer process?
Yeah, there's actually the 10 nanometer process is fantastic. I can't talk about it right now, but I'm doing a lot of work in it for other things that you're not seeing. But the 14 nanometer process, it's mature. We know exactly what it takes to bring that thing out. All the chiplets are mature. The other big thing about FPGAs, it isn't just the devices. The tools have to be mature. So once you bring out a new FPGA, it's got new routing. You've got to make sure that the thing is going to work for everybody. And we're basically reusing the existing routing algorithms, the place and route algorithms in Quartus. So it's not just making the device available, it's making all the tools available from day one.
Right. Okay, thank you. Moshe, I think you mentioned the U50 being a 75 watt card. Just to be clear, what's the availability on your solution?
Once again, what's the availability of our solution?
Yes.
Yeah, so exactly. Our solution is already being tested these days by several potential customers. We are doing POCs to get feedback, to get real life experience with customers. We are planning on general availability December 2020, so end of this year, to give the product, to release it. And later on, start of next year, we will also release it on the cloud.
Okay, great, thank you. And Justin, just I guess on the Bluefield 2X, so I guess that's a 60 TOPS accelerator. We're kind of talking V100 class here, I believe. Is that correct?
Yeah, so we haven't actually announced kind of the performance of that architecture yet, to be honest. And part of that is it's based on Ampere. And so we'll be releasing more, as a performance data soon. But from a power standpoint, I think, you can kind of find inference accelerators from 10 watts, right, with our kind of Xavier NX architecture up to, 400 watts. And for us, like, we see all of those at the edge, because like telco edge, as an example, where they're trying to deliver all these new services over 5G, need a kind of a range of those architectures. So we're working with partners to kind of right size the compute for the problem.
Okay, thanks. And I guess, let me just stick with you for a second here, Justin. I think I was a little confused with the original Bluefield 2X announcement. I'm just trying to understand the positioning or the use cases between the EGX, which is kind of the GPU plus network connectivity, versus Bluefield 2X, which seems more like, I guess, a DPU plus AI. Do I have that right?
That's right. So the way the way people should think about it is, to the host operating system, EGX is two cards that happen to be packaged into one architecture. The host operating system sees a networking card and it's going to see a GPU. The Bluefield 2X, the host operating system just sees a networking card. And the DPU itself is hosting the GPU to apply AI to network traffic, to do traffic shaping and, find new security threats through encrypted data, but you're using AI to look at the packets coming through the network.
Okay, so the Bluefield 2X isn't really intended to be a network connected GPU. As it wouldn't replace an EGX, for example.
That's right. It's you're just using AI for orchestrating the security policies in a dynamic way.
Right. Okay, great. Thank you. Okay, just running through questions here. So Mike, wanted to circle back on your MLPerf numbers.
Sure.
You mentioned the SSD improved 300%,
Right.
between 0.5 and 0.7. And then I think you mentioned AVX 512 was one of the optimizations. Is that how you got there, or what was the kind of the magic bullet on SSD?
Yeah, so that's part of it. So actually in version 0.5, we had already put in many of the AVX 512 optimizations we needed. We did add some more. The biggest problem for us in version 0.5 was TF Lite doesn't have support for batching in the post-processing of MobileNet SSD MobileNet, so all of the NMS operations. And so we were kind of stuck doing everything single-threaded last time. So this time around, we were able to get around that with kind of a different way of parallelizing our TF Lite interpreters and parallelizing that x86 portion that's at the end. So that gives us nearly all of that improvement.
Okay, great, thanks. And while I'm with you here, Mike, Justin mentioned some of the new MLPerf benchmarks. I'm curious if Centaur, you only showed a couple of benchmarks, so has Centaur run BERT or the RNN-T benchmarks, for example?
So this actually goes back to the part of the reason we're switching to our new compiler stack that I presented about. It would have been very difficult to try to support all of those different new benchmarks that are in MLPerf version 0.7. So really, that's what we can focus on now that we have a compiler stack that allows us to much more quickly bring up new networks, including the ones you mentioned, all of the ones that MLPerf includes. So we were actually very close. We were right at the end line for MLPerf, this submission date, almost having SSD ResNet 34 done and running with our new compiler stack, and we just didn't quite get there. So now that we have that, the plan is to support all these much larger, more complicated networks.
Okay, so that brings me to a follow-on on your MLIR discussion. So from a performance standpoint, do you see any sort of performance downside to the added abstraction that's in MLIR?
So as I kind of alluded to, we're at that point now where we have a working system with this new compiler stack. So we haven't yet been able to optimize to match the performance of our old way of doing it. So we don't anticipate that we would have much performance lost, if any, but that'll be what we're exploring really in by the end of this quarter. I imagine we'll have more running, more idea about what performance improvements we need to have or that we're gaining because we have our system that allows us to optimize better. So it's just not clear yet.
Okay. And I think there was a question from an attendee about the framework being open sourced. I think they're referring to MLIR and sort of what portions of that stack. I think you mentioned the kind of the top layer of the stack being an open source project. So what do you expect in terms of in the longer term, how much of that will be open source?
So yeah, we would like to open source all of it if we can. That's something that we will be looking into. The nice thing about this MLIR approach is that there's not necessarily anything that would, prevent any other, company or person from being able to benefit from what we've done, right? I mean, there's nothing Centaur specific really. We're just adding passes and that add functionality and optimizations. There may be a little bit of changes, but we think everybody benefits if everybody kind of contributes to this approach.
Okay, thank you, Mike. Martin, I had a question for you on the DSP block. Can you kind of compare the Stratix NX DSP block with the new DSP in the 10 nanometer AgileX? B, I think Martin is muted. Sorry. B, can you unmute Martin, please? Zoom has added some new, there we go. Zoom has added some new security features.
We could talk about that for hours. How would you like me to summarize that?
Well, so first of all, I mean, the Stratix 10 NX, as I understand it, it's not sort of like you took the AgileX DSP and backported it, right?
No, the AgileX DSP block is really designed for something else. It's the AgileX DSP block is an evolution of the Area 10 and Stratix 10 DSP blocks, where we first put floating point onto the FPGA. So the NX block has, as I showed you, has those 30 multipliers, 30 int 8 multipliers. They can be reconfigured into 60 int 4 multipliers. There's also 3 FP32 adders which they can feed. So there's a lot more density in the block, and there's various ways that we got that greatly increased density. There are certain features that went away. There's no fur filter support directly in there. So if you wanted to build fur filters with the aggregated multipliers, building bigger multipliers, you'd have to put that into soft logic. There's a lot less flexibility in the way the registers are used. The speed of the block was dialed back as well. In Stratix 10, you will need to, you can run the block up to 1 gigahertz. You can't do that in the NX part. It's slower. I can't remember exactly what the different speed grades are. We'll announce that shortly. It's probably about 2/3 that speed. So there's all sorts of things that were done to pack a lot more math in there. Take away some of the flexibility, but add more math.
Okay, great, thank you. Moshe, I just wanted to circle back on one issue. So you talked about training, but didn't mention inference performance. So I'm curious what you expect in terms of inference performance from your solution.
Yeah, so for today, we are running inference about the same rate of T4. So a single U50 can run around the same numbers of T4 for resident, resident 50 and others. But we expect to accelerate it by a factor of 2. Most of our efforts are on accelerating the training part and give the inference, and we are now giving inference more focus. But I would like to emphasize that the inference can also be done by other parties. We are not tying between the training and the inference solution. So inference can be done, by Xilinx solution or by Intel solutions or other inference on FPGAs. Of course, once integrated with our training, then you gain advantages by the fact that you don't need to do any calibration or post-training quantization.
Mm-hmm. Okay. I think, let me just circle back to Justin, and then I'm going to try to get to some panel questions that a little more broadly applicable here. So Justin, you mentioned the transfer learning toolkit. My understanding, I wasn't actually familiar with that until recently. And so my understanding is that's how NVIDIA provides sort of pre-trained models for specific applications. And I assume that that's how you would address the same kinds of enterprise customers that Moshe was talking about, and where you're doing retraining as opposed to training from scratch. Is that correct?
Yeah, I mean, so transfer learning basically takes a pre-trained model where let's say the lower layers of the network aren't trained, right? The model's mostly trained. You can apply it to your data set and you can train those lower layers of the network to complete the network for industry specific use cases. So where that becomes important is like medical imaging, where you've got, regional specific patient data that you need to, take into those regional, differences in terms of, human structure, right? To be able to finalize the AI model for medicine. So that is, taking a pre-trained model and then finalizing the training with regional data. For use cases though, where we're saying, okay, we want to completely train at the edge, we also have frameworks that we call federated learning frameworks. So you have a server that's aggregating the adjusted weights from a distributed set of locations. So you don't have to move the data to a central location. You re-aggregate that model and then send that down, and you kind of retrain in a number of cycles to converge on a unified model that takes into account, all the data that might be distributed across many different locations. So I think there's different techniques, I guess, to training at the edge, depending on what problems ultimately you're trying to solve.
Yeah, so that's a good segue into a question I had for the panel, and I'll start with you on sort of the use cases for federated learning versus this kind of local retraining that Moshe was talking about. Are those really two different sets of customers you see for those two different approaches? Yeah,
we've seen it, well, most of the time I see it used in different scenarios, right? So like the federated learning, a good example would be there's research institutions that want to share patient data, but obviously because of, compliance reasons, they can't move that data to one location. So you'd use federated learning to, start with a central model, push it to, say, 10 different research institutions, train against that data, aggregate the differences, and then you do that in cycles. To then the net effect is as though you had the unified model the unified data to train against. The transfer learning where we see that is, vision AI, for example, like lens distortion on a camera, is different depending on the camera type. And so in some scenarios, you want to retrain the vision model using your own camera data so that you can account for that lens distortion, and that would just be transfer learning. So I think it's going to be dependent on the use case, but those are, I think, two common use cases that we see for federated learning and transfer learning.
Okay, thanks. Moshe, since you're focused on this kind of retraining at the edge, and you guys are, I would say, kind of on the leading edge there in terms of the work you're doing with Int8. Do you see a kind of a killer app being the use case where you'll see early adoption?
Yeah, I think today, from our experience, manufacturing, smart cities, and retail are the three most advanced, domains that are adapted, that are willing to adapt our technology. And I think I would like to connect to what Justin just said. In some cases, even in the retail world, in each branch you have like different sets of products, and in hospital you have like different divisions, and also in the manufacturing, maybe you are a big organization with several manufacturing facilities, and each one of them is specialized in a different product. So the fact that you have like central model does not mean that you want to train over all the examples that you get from all the edge locations. So for example, in the retail world, you would like to do some local training for the examples that are unique to this branch. And another market, another branch, which belongs to the same, to the same organization, but has different products and different type of training applications. So this is just from our experience. We saw that those customers are talking on the same, on the same language that we are talking. They are facing with the difficulties of moving all the data to the one location or the one place that they have all these massive training machines.
Okay, thank you. Mike, you mentioned sort of generalization being one of the advantages of the heterogeneous solution. So what are you seeing in terms of interest in training at the edge?
So our accelerator, our AIC, is for inference. It's not for training. That's not to say, that, we have an expandable platform, right? We could have accelerator cards. You could use x86. Is there more specific about training that you'd like to know about what our technology could be used for?
No, I think I missed the fact that the AIC was specifically designed for inference. So that was my mistake. I guess from a generalization standpoint, you've got AVX 512 support. You can support essentially any model that'll run on an x86, and it's a question of what you're able to accelerate.
So that's a great question. So it actually dovetails right in with this MLIR approach, because before, with our oldest stack, what we'd have to do is support almost the entire network before we could run anything for that network. With this new approach, we can much more easily just support, say, one operation in an entire model first, and then just sort of expand out from there. Mm-hmm. So, which is great because we do have x86, so everything that we are not ready to support in AIC yet, we can just offload to x86 and slowly bring up whatever we need to first. So it actually is really great for just the development effort as well. Yeah.
So, I mean, the model works. It's a question of performance as opposed to saying, nope, it doesn't work at all. And
absolutely, yeah.
There is an attendee question that kind of ties into this, and that's a question regarding support for AMX. Is that something that you see on your roadmap?
So AMX clearly was announced after we've been using this chip. So it's obviously not in this chip. So looking at AMX, the first comment I'd like to make about that is when you start adding things like that into the general purpose logic, you do start to complicate that logic, right? So I think that there's a clear advantage to having an on-chip but separate, distinct accelerator for this. I'm not sure it's clear what performance can be expected from AMX compared to like our AIC, for example, but I think the win will be integrated accelerators for neural networks instead.
Mm-hmm. Okay, thanks. So I want to circle back to the issue of MLPerf, and I'll start with you, Mike, since I've got you engaged here. So I've heard some criticism of MLPerf as being useful as a baseline, but not kind of real world. I think Pete, our keynote speaker, mentioned very rapid model adoption. But on the other hand, Moshe was talking about kind of stable models being deployed by these more enterprise class customers. So I'm interested in your view, Mike, and is it really a question of different kinds of end customers? Obviously, hyperscalers might be developing their own models versus some of the more edge-oriented enterprise customers using kind of more static, stable, kind of off-the-shelf pre-trained models.
So I think that's front and center, right? Like I think that's a huge thing that everybody's thinking about right now. Some people do want the latest edge models for everything, even if it's not being used anywhere. It's nice as a smaller company, right? It's nice if we can use something where there's already precedent for it being run somewhere on x86 or somewhere first, having some sort of adoption for it, something where it's clear that there will be a customer that wants to use it. So yes, I think that's a valid question, and I don't think there's an answer to it yet. I think it's part of the discussion and part of the debate that's ongoing right now. That being said, I think MLPerf has done a really good job going from a very limited number of benchmarks in version 0.5 to a much larger number this time around in version 0.7. And they're constantly reaching out to industry to see what is being used and trying to really make it a good benchmark, a good baseline for anybody who wants to do ML workloads.
Mm-hmm. Justin, you mentioned some of the new benchmarks. What's your view on this issue of kind of real world versus always chasing the latest and greatest models? Justin is muted again. Let's see if we can get this.
Sorry, it's a habit, on these calls to like put yourself on mute so you don't hear any background noise.
Yeah, well, you used to be able to unmute yourself, and for some reason we seem to have lost that control. So
yeah, so I think like we like our view on this is like accelerators are needed to be able to accelerate everything, right? And we are trying to accelerate the widest domain of models and applications with GPUs, and that's kind of been our business for the last 25 years, is to chase all of the important applications, tune them, and optimize them for architecture. So the nice thing about MLPerf though is they are, I'd say, industry contributed models. They're peer reviewed, so that it's not like people are playing with the I'll say playing with the models to tune them to their architecture only or to favor their architecture. So it seems like MLPerf gives you kind of a good cross section of common uses of AI run across a bunch of architectures, and it kind of highlights the maturity of the software, right? And we're always kind of big proponents of that AI is a full stack computing problem. And it's all about all the work in software in addition to having these great chip architectures. There's just a ton of work that has to go into compilers and development tools and the developer ecosystem, and then making it easier for developers to engage these new architectures.
Okay. I'll throw a couple software questions at you while we're on this subject. We've got a couple audience questions. One was, can NVIDIA GPUs work with the RISC-V architecture?
So we don't have like CUDA on RISC-V that NVIDIA supports, but we do have an open source project called NVDLA that gives you IP blocks that you can build into a RISC architecture. So I think that's the only practical way to get going on a RISC-V architecture today. Where we support kind of CUDA on architectures, we'll support CUDA on x86, obviously, and CUDA on ARM are the two predominant ISAs that we support that full software stack on.
Okay, and then on the Bluefield side, there's an audience question about who's developing the software for Bluefield. I guess I think really the question is what level of software do you provide for Bluefield?
Yeah, so Bluefield, we created this programming model called Doka, and Doka is a parallel to CUDA. Underneath Doka, there's, I'd say, industry standard APIs that we started with in just accelerating those. So APIs like DPDK for Data Plane Developer Kit or SPDK for storage. We also are obviously looking at programming models like P4, but P4 as a programming model feels more vendor driven than customer driven, but we can accelerate that just as I'd say just as good as anybody else. So we want to kind of meet developers where they are today with DPDK and SPDK, and then see how to enhance those programming models as we go forward under this umbrella we call Doka. So I mean, expect us to, just like we did with GPUs many years ago, we obviously with graphics had to support all the open industry standards with DirectX or OpenGL, and then we would look at extensions to those programming models that basically highlight the architectural benefits of our processor. So we'll do the same thing with the Doka programming model.
Okay, got it. Thank you. Martin, I wanted to circle back to you, and we'll see if others have input here. But you specifically mentioned Int4. So I'm interested in hearing your perspective on where we are with adoption of Int4 for inference.
What's the best way of saying that? It's easy for us to support it. We see that there is movement to that. We're seeing that from our customers. If we built the Int8, it was essentially trivial for us to build the Int4. We had a certain budget, both time and area. We were able to do Int4. It's available for everybody. Plus the floating point works, the shared floating point exponent works with the Int4. So we're going to put it out there and see what happens. Some of our customers wanted that very specifically.
Okay, thanks. Mike, any input on Int4, or you're getting most of the bang for the buck out of Int8 and not a lot of pull there?
So I'd actually put that question to my colleague who's on this panel as well, Parviz Palangpour. He's our team lead. He's an expert at this. Parviz, are you there?
Yeah, so I would say for us, it's really challenging to bring up the entire ecosystem to do training in Int4. I know a lot of frameworks have some tooling to support it, but as far as working for a really wide range of models, we're focused on Int8. There's even cases where Int8 has some challenges, so we haven't focused too heavily on Int4 yet.
Okay, thanks. Justin, you have anything to add on kind of the research in the area of Int4?
Okay. Yeah, I mean, I think, so our new architectures like A100 support Int4 and Turing support Int4. And, we've kind of created this automatic mixed precision compiler basically to try and use to not reduce accuracy and basically move to the lowest precision possible just to increase pipeline throughput. So I think we will keep tuning and supporting all the way down to lower precisions, but we're kind of going where the market goes, I guess, and trying to support everything.
Yeah, I think Moshe, you mentioned you felt most customers were still training using FP32 rather than mixed precision. What was the reason behind that?
I think some customers tried, it's what we heard, yes, and also our internal experiment is that mixed precision can work for certain networks, and for others you need to do some manual tuning in order to make it work in a similar way to what we are doing on Int8, because once you take the precision down, you have to compensate in some sense. And for most of the customers, what they are focused on getting the best results that they can in the shortest time, they found that it's not worth the effort to go in this direction. They prefer to spend more cycles on the FP32 and just finish the training knowing that this is the best result that they can achieve. let me just add a few more words about the Int4 that you asked. We've seen some customers that are working in Int4 for inference, but all those examples were in situations that the accuracy was not their major concern. So they could lose few percent for doing Int4 and it was fine. But clearly, if inference at Int4 can maintain accuracy, then it would be very interesting to many customers. And the nice thing about FPGA is but since you can reprogram the FPGA, you can start the training doing like even floating point in Martin's situation. You can do floating point and later on do int8 training, and towards the end of the training, get the system to adapt to the int4 that will be eventually on the inference. So you can do it in several steps, and you can switch the bitstream. You can switch the hardware that's doing the acceleration part during the training.
Okay, thanks for that. Justin, did you want to follow up on the issue of mixed precision versus FP32? And I guess more generally speaking, what's NVIDIA's approach to kind of accelerating training times?
Yeah, I mean, I think, one of the big things that we focused on in the A100 architecture was sparsity and basically taking advantage of sparsity to accelerate training times. And so, the architecture supports a number of different precisions. So FP32, FP16, we've got a new precision called bfloat 16. And ultimately, I'm not the, I guess the accuracy and training research guru that some of the panel are, but ultimately, we're just trying to get, I'm not trying to say, highly accurate models as fast as possible and keep tuning kind of all the frameworks to use all of these latest techniques and kind of let the industry decide what are the right rulers, right, to use in terms of measuring the accuracy of the models and training the models, and then ultimately using the inference engines for edge computing.
Right. Okay. Let me try to get to a couple of audience questions here before we run out of time. I think there was a question for Mike regarding DRAM bandwidth and how you avoid kind of contention for memory bandwidth and causing higher latency on your accelerator.
Sure, absolutely. So, I mean, you have the bandwidth that you have. If generally speaking, x86 workloads are going to be, you have enough of them going on that you're going to have somewhat uniform channel usage there. And so as long as we're also using the channels uniformly, we're going to have as much bandwidth being used as possible. That being said, if you really need all of the DDR bandwidth for the accelerator, then you better know what other workloads are going on x86 and plan for that. So we put a lot of effort into making sure that our architecture can use all the bandwidth that it possibly can as well. It's I think it's just an optimization question for x86 at that point, I believe. I mean, you try to use your cache as much as you can and be smart and know what you're running.
Thanks. Martin, there's a related memory question, but this one's on capacity. Can you tell us what the effective capacity is for weights and activations on the Stratix 10NX?
Yeah, so there's two different types of memory that you'd most likely use for that. There's the 7,000 approximately M20Ks that would work out to be about 135 megabits. That's distributed across the FPGA die. Very easy to get to the AI tensor blocks. And then there's going to be 1 or 2 stacks of 8 gigabyte HBM2 that can be directly accessed. There's some other memory on board, but those are the two main memories you're going to use depending if you want basically a local memory or a large memory.
Got it. Okay. I think there was kind of a detailed question here on spec-int numbers. I think that was referring to Justin's roadmap. I guess, Justin, is there anything you want to add regarding the kind of the Bluefield roadmap and where you see that going from a CPU performance standpoint?
Yeah, I mean, I think, and just to close this off, because you asked all these great questions on, Bluefield 2X versus a discrete GPU and a network card on the same architecture. So these architectures are really used. The best way to think of it is for offloading the CPUs for software-defined networking, software-defined security, management, types of use cases, right? And so there's use cases where you want to do just the software-defined networking on the Bluefield 2, and the ARM cores give you the ability to, like if you change, the SDN, it's a orchestration in a way that isn't optimized in the silicon of ConnectX-6, to add those features in ARM cores, and we see that happening a lot in cloud providers, where they basically, they don't want their infrastructure services to compete with the CPU cycles of a tenant coming into the infrastructure. And so that's kind of the role of the DPU. But more and more, just like I'll say AWS is a good example. AWS bought Annapurna and then built the Nitro architecture, and the Nitro architecture added a security layer to the core infrastructure. They had what they call VPC offloads in an architecture that was running on something like Bluefield. They had EBS storage, which is delivered on an architecture like Bluefield. More and more of those use cases we see moving to these architectures that go into core enterprise data centers for the same security reasons. And they're obviously to support more concurrent VMs with emulated storage that's running on these architectures, they need more CPU cores. So we're going to keep kind of increasing the performance on the CPU side, which were those spec int numbers. Just as every, I'd say, AI accelerator today has both, CPUs, GPUs, and networking, we think there's a tremendous value to adding the tensor cores to the DPU so that you can use basically a computer in front of your computer to look at the network traffic using AI, and then you can basically apply firewall rules and hardware to drop those packets before they impact the x86 cycles that might be doing compute. So that's going to become, I think, a core tenet of every enterprise data center is to have, I'd say, this hardening of their infrastructure, where instead of having your network security at the perimeter, you have it at the edge of every node.
Okay, thanks for that. Useful view on the big picture there. With that, I think we have run out of time. So I'd like to thank our panel for a good discussion. And I think we got to most of the audience questions. For those that we didn't get to, we'll have breakout sessions with Centaur, Intel, and Deep AI, as well as the Google keynote speaker from this morning. The attendees should have received an email with links to the breakout sessions. So if you look for those separate links, you can attend any of the breakout sessions that are taking place. So give our speakers just a couple minutes to transition over to those Zoom sessions, and we will hopefully see you over there. So thanks again to our panel, and that's the end of our conference sessions for today.